Welcome to our class, Engineering Mechanics 2. Today, we will practice several examples from Chapter 4. We'll start practicing the Chapter 4 problems. Of course, it's a bigger chapter again, discussing the point kinetics. We talked about the theory and started discussing the first exercise of this chapter, exercise 4.1. Which you can see right here. And now we already did the free body diagram. We have the normal forces on both wheels, back wheel and front wheel. We have the force of gravity in the center of the car. We have the driving force as described in the problem on the back wheel, and we have the inertial force acting in opposite direction to the acceleration. And now we can start solving the problem. Again, the friction coefficient is only given at the back wheel, and this indicates that we can neglect the force of friction on the front wheel. Force of friction is significantly higher on the back wheel due to the driving force acting on this wheel, on this axis, and that's why we can neglect friction on the front wheel, but of course there is still a normal force on the front wheel. Now, we have the equation for static friction, which is stated right here. And we can build the dynamic equilibrium conditions. And building dynamic equilibrium condition works the same way as in statics. The only difference here is that we have this additional force, this inertial force in our system. Now, there are two questions, two parts of the question. First one is to find the maximum acceleration for the car when the back wheel just does not slip. So it's the limiting case, meaning that we still have static friction, maximum acceleration, to obtain static friction. And the second question, that we have to find the acceleration in the case that the front wheels are lifted from the ground. Okay, now you have time to solve the problem. Answer two questions. First of all, the maximum acceleration in case of static friction, and second question, maximum acceleration when the front wheels are lifted. Of course, in the second question, the acceleration has to be higher than in the previous part of the problem, meaning that then we do not have static friction anymore. The back wheels will slip. Okay, I open the breakout sessions. If you have any questions, please ask me, call me into your session, or solve it on your own and call me into a session that is empty or small, as you prefer. Ask me in the main room. Doesn't matter, but please try to solve the problem discussing with your classmates or on your own as you prefer. And then I will present the final solution. I will not derive all equations the whole way through. I will give you the main parts, and if you have any trouble solving the problems, then you can ask specific questions and I will help you there. Okay, any questions before we start? Okay, if not, I'll open the sessions and you can choose your session and start working on the exercise.
Hello, Prof. Hello, Prof. Uh,
Okay, are there any questions here?
Yeah, I have a question.
Okay.
Concerning the free body diagram you gave, you made, and the first question said we should determine the acceleration if it wasn't sliding. So when I tried getting my equation out of the forces out of the equation, when I saw the free body diagram you gave, you made known of the two tires, giving the forces of each tires. For the first question, do that forces matter? Because I don't know
Are you talking about the normal forces?
the normal forces from the tires itself,
Yes.
the tires of the vehicle. Do they matter? Like, because normally I took them as one, but you separated
No,
them.
you can't. You can't take them as one. They do matter. They do have an effect on the system and the size of these forces. Otherwise, if you do not know the normal forces, you wouldn't be able to compute the acceleration because
So
you do
does
not
that
know the force of friction.
okay? Does that give us because it changes the whole equation? Then friction should be mu into bracket ns plus nf.
No, the friction acts on the back wheel, so it's only the normal force on the back wheel in this equation.
Oh, okay.
So Fr is smaller or equal to mu0 times n back wheel.
Okay.
And then you have to derive the normal force on the back wheel.
Okay. Thank you very much, ma'am.
Yep. Okay, are there other questions? Okay, well, the students in the groups, they still need some time to solve the problem. Most of them have solved the first part. I assume you did that too. So there's only the second part of the question missing. So let's say until 10 past 12, and then we can have a look at the solution.
Okay, ma'am.
All right. Okay, let's have a look at the solution. So that's where we started. We have the static friction equation. Of course, if the force of friction acts on the back wheel, then there's only the normal force acting on the back wheel relevant in this equation. So this is our equation number one, the first equation we need to solve the problem, and then we can build the dynamic equilibrium conditions. Here, the horizontal equilibrium condition and the moment with respect to the front wheel are enough. We do not need the sum of all forces in vertical direction. And then we can substitute the force of friction from equation 2 into equation number 1 and the normal force on the back wheel in equation 1 as well, and rearrange the equation and obtain the acceleration, maximum acceleration of 3.98 meter per second, maximum acceleration when the back wheel just does not slip. Okay, so that's the first part that you should have obtained, the solution you should have obtained for the first part of this problem. And in the second part, it's asked for the acceleration for which the front wheels are lifted from the ground. If the front wheel is lifted from the ground, there's no normal force acting on the front wheel because there's no connection between front wheel and surface and road anymore. Which means that in that case, the normal force is equal to 0. We can build the equilibrium condition with respect to the back wheel, rearrange the equation, and obtain the acceleration in case of liftoff with 17.8 meter per second. And of course, in this case, the acceleration is greater than before, meaning that the back wheel is slipping. And if the back wheel is slipping, then our equation number 1 for the force of friction cannot be used anymore, cannot be applied because there is no static friction on this back wheel. Okay.
Professor, I have a question.
Yes.
Why is, can you scroll up the diagram?
Yeah.
Why is MA in the backward direction? Like, isn't it accelerating forwards?
The acceleration is acting forward, and on Friday we discussed that the inertial force m times a has to act opposite to the direction of acceleration. So opposite to a, because it's an inertial force.
Okay.
The inertia of the car acting against the change of motion.
Okay, yeah, I got it. Thank you.
Okay, yep. Other questions?
I have a question. I understood the part whereby you FR is equals to MA based on the diagram. Then, of course, FR is also equals to mu naught over MB. And we know that MB is also equals to MG. Well, I didn't get...
No, NB is not equal to MG. That's wrong.
Okay.
If you build the equation in vertical direction, then you'd have NB plus NF minus MG.
Okay.
You have to use this equation right here.
Okay.
Yeah, I'm sorry. And regarding this equation, to be honest, I stuck on the moment where I had to find the normal force in the rear wheels. And I think this is the equation of the moment, but about what point?
The front wheel.
Okay.
That's why I wrote F here, front wheel.
Okay. Mm-hmm.
Mm. And you have the dimensions given, S and L, and the height. And then you can derive the equation. So with respect to this point right here. Sorry, front wheel.
Yes.
This point right here to get the back wheel. Okay.
Can you please derive?
So I just okay again.
Yeah, the last line of your solution.
Equation number 3.
No. Regarding the second part of
yes.
the problem.
Okay. I substituted MA here for FR.
Yes.
It's positive because here in this case, if I would have chosen FR pointing the opposite direction, then I would have had to build the absolute value, and MA would have become positive again. So it wouldn't have mattered in case of static friction. It doesn't matter whether we chose the correct direction of the force of friction or not. Of course.
Yeah, I mean
yes,
the
I know you're a
second
step
part.
further. Then I used this
Okay.
and substituted in here.
Yes.
And then I rearranged for the acceleration. You cancel the mass, and then you just simply rearrange.
Yeah, I mean, I meant the second part.
You're
of the
stuck with the
problem.
mathematics.
No. I'm talking about the second part of the problem.
Oh,
with the,
okay, sorry.
With the wheels
Lift off.
in the
Okay,
air. Yes,
okay,
yes.
now I got you. All right.
No problem.
So here the normal force on the front wheel is 0, right?
Yes, right.
Then
because we're in the air.
in the case of liftoff, then I built so it's simply this diagram here without this force. And then I used this point for the equation of momentum. And then there's only MA and MG in the equation.
Yes, now I see. You use the back wheel as the
yes,
point of rotation. Okay.
Exactly.
Yes, perfect. Thank you.
Yeah, you're welcome.
Oh, one last question, Prof.
Yes.
Concerning that equation 3, I still don't get that part where we use M over L over into bracket GS plus AH.
Well, I just built the equation. The equation of momentum with respect to the front wheel. 0 is equal to, then you have NB, the normal force on the back wheel, times L. Force of friction has no effect, and but gravity in opposite direction minus mg, and the distance is s, and minus ma with height h. And then you rearrange the equation for NB, divide by L.
Sorry, I still don't get that part.
What is it that you don't get?
NB and NF are normal reactions and their forces. Multiplying it with their length, is it not in form of like a moment, or I don't know?
Yes, it's like in statics, building the equation of momentum
with
respect to a specific point, and in this case, we chose the front wheel.
Okay.
As the point of rotation.
Okay. Thank you, ma.
Okay. Okay. Other questions? Okay, if not, then let's move on to the next problem. It's still special case number 1, rectilinear motion of point masses. Problem 4.6. So what do we have here? We have 2 identical masses, which are given in size, and they are positioned on a pulley. And we have to find the accelerations of the masses when they start to move. So the whole system is at rest, and then the masses are released. The system, probably mass M2, is released, and then the system starts to move. The mass M2 moves downwards, as depicted. And the pulley wheels itself are assumed to be massless. So that simplifies our problem for the start. And we have to find the rope forces as well. So what do we have to do? Of course, again, we have to start with our free body diagram. One free body diagram for every object, every mass, every system, subsystem. So, but before we do that, we have to understand how the system moves. And that's really important in dynamics, because if you do not understand the kind of motion, the direction of the motion, then you're not able to define the inertial force correctly. Okay, so in this case, we know that mass M2 moves downward, and mass M2 is connected to a rope, and the rope is guided over the pulleys until here, where it's fixed in the wall. And now the mass moves downward and the rope moves over the pulley, then the pulley has to rotate in this direction. Rotation, oh, well, if you talk about accelerations, then it would be alpha. Let's call this pulley number 2, and then this is alpha 2. And this is pulley number 1. Then the rope moves over the first pulley, the pulley on the left. And then this means that this pulley has to rotate in this direction with alpha 1. And at the same time, this pulley number 1 moves upwards. It moves upwards with the same acceleration as the mass m1, since the mass is connected to the pulley, to the center of the pulley. So they have the same acceleration. Translational component of pulley 1 is equal to the absolute acceleration of the mass m1. Okay. Any questions so far? All right. Once we understood the motion, the direction of the motion, we can derive the kinematic conditions. So that's what we will do next. Now, what do we know? We know the acceleration a2 of the mass. And we know that the second pulley rotates, and the rope that moves over the pulley 2 has to be of same length as the rope that moves the mass m2 downwards. Okay, I will draw another figure because I think usually it's easier to understand the motion and derive the kinematic condition if we know the distances traveled. I think it's easier describing it using distances traveled instead of accelerations or velocities maybe. So okay, let's say this mass moves downward a certain distance x2. Now the rope traveling over the pulley number 2 has to be of same distance. So the arc length covered by the pulley is equal to the distance of the mass x2 moving downwards. So we can state that x2 is equal to r times phi 2, assuming that these have a radius r. Okay, that's our first kinematic condition. Now, let's move on to the second pulley. The second pulley is here. Now our rope moves over the pulley and up here, and it's fixed here. Now, pulley number 1 rotates with phi 1, and the center of the pulley, or the pulley itself, moves upwards with x1. Now, the rope on the left is fixed to the ceiling of the system. This means that the velocity in this point right here, the absolute velocity, is equal to 0. And this absolute velocity in this point consists of translation, or the absolute distance traveled, if you talk about distances, as equal to translation plus rotation, as we learned in chapter 1, x1 and r phi 1. Then we have our second kinematic condition, x1 is equal to r phi 1, pure rolling. If you rotate the system by 90 degrees, the rope on the left would be the ground, the surface, the non-moving surface, and the pulley number 1 would perform a pure rolling motion. Okay, and of course the mass M1 is connected here, and as we already said, this moves with the same x1. So there's no additional kinematic condition that we have to derive if we use the same variables. Okay. But what we still need is a relation between pulley 1 and pulley 2. So what do we know? We know that pulley 2 moves due to pure rotation, wrong color, r times phi 2. That's the motion of pulley 2. And we have a rope connecting both pulleys, a rope under tension, and then this has to be equal to the absolute motion of pulley number 1, which consists of translation and rotation. And these are our 3 kinematic conditions. Now, we know that we need 3 kinematic conditions by counting the kinematic variables. So our kinematic variables in terms of distances are x1, phi1, phi2, and x2. Okay.
Professor, can you explain again the last equation, r phi 2 equals x1 and plus r phi 1?
Yes, just a second. So we have 4 kinematic variables. And since this is a system in motion, we need 1 kinematic condition less than the number of our kinematic variables. In the specific case, we have 4 kinematic variables, so we need 3 kinematic conditions. Of course, we could add another variable by when we distinguish between the mass, the motion of the mass M1, and the pulley 1, then we could call this x. We have left x3. Then we would have a 5th kinematic variable and a 4th kinematic condition x1 is equal to x3. But in this case, then since the pulleys are massless, this is not necessary. Okay, let's come back to this kinematic condition. We are comparing pulley 1 to pulley 2. Pulley 2 performs a pure rotational motion since the center of this pulley is fixed due to the rope being connected to the ceiling. So this pulley, how much rope is moving over the pulley? The distance of the rope covered corresponds to r times phi 2. This is the amount of rope moving over the pulley in a certain time interval. So how much rope moves upwards between these 2 pulleys? Well, this consists of 2 parts, 2 components. We have the translational motion of the pulley 1, since it moves upwards. So this is x1. And we have the rotational motion of pulley 1 due to the rotation. So there's also rope moving upwards. Then we have to add these 2 components to obtain the absolute motion of pulley 1 and of the rope moving over pulley 1. And that's why it's x1 plus r times phi 1.
Okay.
Mm-hmm. Now, we want to describe the accelerations of the 2 masses, A1 and A2. And that means that we have to derive our kinematic conditions in terms of these 2 accelerations, and they should depend on these 2 accelerations. So for the first one, we can also state that A2 is equal to R alpha 2. Same here for A1 alpha 1. And here we can substitute this relation here then this is equal to 2x2. And this leads to R alpha 2 is equal to 2A2, A1. And then again, we can use this relation right here and substitute R times alpha. And we obtain A2 is equal to 2A1. And now we have expressed the acceleration A2 in terms of the acceleration A1. Like the problems we did at the end of chapter 2, talking about kinematic conditions. Okay? And once we know that, we can start solving the problem, the kinetics, talking about forces, etc.
Professor,
Yes.
I have a question. Could I annotate a little bit?
Okay.
Okay. If I try to find the equation for the rope, like I took a function from it, the length of the rope, like here it's x1, here it's x1, 2x1 equal to 2x2, this length, then I could differentiate one time to get the velocity, second time to get the acceleration, and we get, same acceleration equation.
Well, it's not the length of the rope, but it's the distance the rope travels. So, for example, you could pick a point here, here, and the point of the rope here, for example. So the question would be, how far does the rope travel in this situation up to here, which depends on the two types, x1 plus r phi 1. You can draw these vectors on this side as well. You have to change direction of the rotational component, and this has to correspond to the distance the rope travels on this side of the pulley.
Yeah, understood. Thank you.
Yeah. Okay.
Professor, I have a question.
Yes.
A1 is the acceleration of the mass 1, right?
Yes, here.
Okay, but why is it a R alpha 1? I thought it should be 2 times R alpha 1 because the pulley is rotating and also translating, which is
yes, but the mass is connected to the center of the pulley. So only the translational component is of relevance.
Okay.
Okay, so if you rotate the whole system and your rope would become the surface, then it rotates and translates in this direction. And then this point right here in the center only moves due to translation.
Okay. Okay, that's clear.
Yeah? Then this would be here later on, and this would be the distance x traveled, only the distance x. But if you describe, for example, this point right here, then it would be here later on, and then this distance here consists of translation and rotation.
Okay. Yeah, it makes sense now. Yeah.
Okay.
Thanks.
Yep. Question in the chat. I simply used this kinematic condition right here and substituted R phi 1 in this point, and then we obtained that equation. And then by building the second time derivative, we can express this relation in terms of accelerations. Okay. Once we have the kinematic conditions, we can start solving and we can start drawing the free body diagrams. So in this case, we have 4 subsystems, meaning that we can draw a free body diagram for every pulley and for the two masses. Mass 2, mass 1. Now, in case that the pulleys are massless, our tension in the rope is of same size of the pull on both sides of the pulley. If the pulley would have a mass, then this is not true anymore. Then we would have a different tension on the left and on the right. But right now, we are only talking about point masses, and then our pulley has, to simplify the problem, has no mass at all. Then we can neglect this part and assume that the tension in the rope is of same size. Okay, but first rope we have is this one right here, connection between mass M1 and the first pulley. Then we have the tension here. Then we have to cut through the rope on this side. And as I just said, the tension is of same size here and then here. Oops, that's a T, should be a T as well. Then there's a third rope right here. And we have to consider the force of gravity for both masses, M1G, M2G, and we have to consider the inertial force acting opposite to the direction of acceleration. So the second mass moves downwards, it's accelerated downwards, and then the inertial force has to act opposite, upwards, pointing upwards. And for the first mass moves upwards, then the inertial force has to act downwards. And that's it. If you're not sure about the tension, whether they are of same size or not on both sides of the pulley, you could just pick different sizes. Okay, for example, for the upper pulley, what we could have done is stated that this is T2, T3, and T4. And then if we build the equilibrium condition, equation of momentum with respect to the center of the pulley, then we would obtain 0 is equal to 2T2 minus times R minus T4 times R, and this would result in the following, stating that the tensions are of same size. So if you're unsure, then simply assume different forces, and then your equations will show you whether they are of same size or not.
Excuse me, Prof.
Yes.
I have a question.
Yeah, go ahead.
Sorry, concerning the direction of mass of the acceleration for M2.
Yes.
You said that it was moving up. It shouldn't be moving down? And
no, the
M1
mass
up.
the mass M2 is moving down and the mass M1 is moving up.
Oh, okay. Because based on
That's
the
given,
original diagram,
that's given in the problem description, exactly.
Yeah.
Okay.
Yes.
Okay. So once you have the free body diagrams, you can start solving the system, building the equilibrium conditions. Of course, they are quite simple here. since we already know that the tensions are of same size, we do not have to build the equation of momentum. We do not have to build the sum of forces in horizontal direction. So there's only 4 equations for the 4 in total for the 4 free body diagrams. Then we rearrange the equation to find A1, A2, and the tension T1, T2, and T3. Okay, so try to solve the system, state the equilibrium conditions, and rearrange the equations. And I'll open the breakout sessions. If you have a question, then let me know. The masses are given as follows: m1 is equal to m2 is equal to m. So you could neglect the indices of the masses and simply state ma2 and ma1. Okay.
Prof, I have a question.
Yes, go ahead.
It's concerning this acceleration. I'm kind of actually getting a problem based on the direction. Now, in the question that you wrote in green marker, you said it was A1 which is moving upwards.
Yes.
So, of course, the weight itself, M1G, will always act downwards because it's weight due to acceleration due to
Yes.
gravity. Now, but in here again, the M1A1, you still said it's going to go downwards. Shouldn't it be upwards? Because now when A1 is moving upwards, M1A1 is moving downwards.
No, that's just what we discussed in the previous example and on our Friday class. The MA1 is an inertial force and it acts against the change of motion. So it always acts opposite to the acceleration. So if A moves upwards, MA1 has to move downward, opposite to A1, opposite to the acceleration.
I didn't get, I'll note that down. Thank you very much, ma.
Yeah, all right. Okay, everybody's back, so let's have a look at the solution. Okay, so I think the most difficult part is deriving the kinematic conditions, since you're not that much used to it so far. And then once we have them and we have the free body diagram, solving the problem should have been simple. We have 4 equations, 1 for every free body diagram, and I rearranged them for the tension. We can substitute the kinematic condition and then solve for the acceleration A1. And once we have that acceleration, we use the kinematic condition to obtain the acceleration A2. And knowing the acceleration, we can go back to our equations 1 and 2 and solve for the tensions. So tension in row 1 and 3 should be 1.2 mg, and in row 2 should be 0.6 mg. Okay. And of course, acceleration, the acceleration of the mass m2 is twice as big as the acceleration of mass m1, since it consists of translation and rotation of pulley 1, while the acceleration, the motion of mass m1 only consists of the translational component of the absolute acceleration, the absolute motion of the pulley m1. Okay, any questions? Okay, if not, then I hope you are able to derive this problem, to derive the solution. And then we still have a few minutes left. So if you do not have any questions, I would like to start with the next exercise. And that is exercise 4.3. So okay, there it is. So what do we have? We have an object in free fall. And the air resistance is given with this equation. The drag coefficient is given as well, same equation as in the bike problem, of course. And we have to find the relation between falling time and velocity, relation between these two variables, meaning that we have to derive the velocity as time-dependent variable. And we have to find the final velocity that the object reaches, assuming that the height where it starts the free fall is big enough. Okay, well, the free body diagram is quite simple. Let's assume it's a ball in free fall, our point mass, and we know that it moves downwards, so our velocity and acceleration distance as well, of course, point downward. We have a mass, well, the object has a mass, so we have force of gravity, have to consider the force of gravity. We have to consider the inertial force acting opposite to the acceleration. So again, it's acting upwards. And we have to consider the air resistance, also acting against the motion, opposite to the direction of motion, F. W is what it's called here. Okay, now you can start building the equilibrium condition, rearranging the equation for the acceleration, and how to solve this is what we will discuss later on. But what you can do now is you can solve for the final velocity. So try to answer the second question first, because it's a much simpler, easier to answer that question. So how big is the final velocity of that object? Okay. It's so like 5 minutes, and then we have a look at the solution. Okay, I think this should have been quickly solved. So the only thing that we have to understand is when we reach the final velocity, maximum velocity of the system, and there's no acceleration in the system anymore. So it's not being accelerated. And if it's not being accelerated, then the inertial force is equal to 0 due to the fact the acceleration is 0. And then there are only two forces in the equation, gravity and air resistance. And then we can rearrange this equation for the velocity and obtain the final velocity v and as being equal to the square root of mg over k. Okay. For the first part of the problem, we will this will take a bit more time solving this, and we will do this together in our Friday's class. And then we'll have a look at an example of an object in free fall to get a feeling for the final velocity and how big it might be, depending on the situation, of course. Okay, any questions? Well, if not, then I would like to stop here. I wish you a good week, and we continue with this problem and some more problems, exercises, of course, in our class on Friday. Dan, have a good week, and bye.
Thank you, Professor. Goodbye.
Thanks. Goodbye.